Hello, everyone. Making it this far is good. So first of all, congratulations. And now let's look at exercise number 12, which is concerned with the so-called Goddard rocket environment or experiment. So what is the actual problem that we will look at today? It's a rocket like this, but much simplified, so to say. A rocket has the problem, it has fuel, or it needs fuel in order to increase its velocity. But while doing so, it loses fuel, so it loses mass. Less mass is easier to accelerate, but also losing fuel is bad because then you don't have the availability of accelerating later on. And this is a problem that we know from engineering, from rockets, where you, of course, have the task to leave the atmosphere. So it is actually an optimization problem where you have to decide when to accelerate and how much to accelerate and when not. And this makes it a kind of perfect fit for a reinforcement learning problem. So what are the states that we will be looking at in this environment? We have a pointing stick somewhere. It doesn't matter, arms are long enough. So I think it was one line above. So yes, the states that we are going to look at are vertical position, the velocity, so vertical velocity, of course, then of the rocket, and the mass of the rocket, so which translates to how much fuel we have left, kind of. And of course, simplified, or the scenarios and so far already simplified that we are only looking at one dimension. So the rocket is going straight up. We are not looking at any other directions here, so to say. Yeah. And our action that we can take is just how much we throttle, so to say. So if we try to accelerate with full speed or zero or anything in between. So we have a continuous state space, we have a continuous action space. And our first task is to have a look at this problem using DDPG, which is, what is it? DDPG, without reading, who can tell me what this abbreviation stands for? Exactly, deep deterministic policy gradient. So, deterministic policy gradient. Is this a stochastic policy that falls out there? No, it's not. It's a deterministic policy that we get out of that, which is, for technical problems, actually what we want, because we expect that the optimal solution that we are searching for is deterministic anyway, right? So we are not losing out on anything. Although the more general case is having a stochastic policy, because a deterministic policy is just a stochastic policy with the variance reduced to zero, right? So if I have a deterministic policy, I can always integrate it into a stochastic policy. It doesn't work the other way around. So if you want to solve a stochastic problem, DDPG is not the way to go, but if you're coming from the technical side, then deterministic policies is usually what you want. So DDPG is closely related to actor-critic algorithm, which you've already seen. So maybe can someone tell me what are the components of an actor-critic algorithm?
Basically, we have the critic, which estimates the state action values, and we have the actor, which optimizes the policy based on the estimations by the critic.
Exactly. So let's just put two boxes here. We have actor, we have critic. In actor critic, so first scenario, actor critic. This is kind of a review, what we did so far, actor critic. So what is the input of the actor? What goes in here? The states and actions? Only states, yeah, exactly. So either states, or we could also say observations, if observations are not the same as states. But yeah, basically the states go into the actor, and what goes out of the actor? The action, exactly. So A, or if you're coming from control, then the action is usually called U. So this is task of the actor. You throw in where you are, which is the state of your environment, and you get out what you should do, the action that you should take in your environment. How about the critic? What goes into the critic for actor-critic algorithm? Also the observations or states, exactly. So X. And what goes out? The Q values. Are you sure? Sorry? No. No, the actions already we get from the actor. It's the state value function. So V of X. State value, not action value, not Q, but V for actor-critic algorithm. And the good thing about this algorithm is we can use it to learn a stochastic policy. But as I just said, for many cases, there's actually no practical need for a stochastic policy. If you want to play poker, stochastic policy is good, because if you're always acting deterministically, then someone else could know what you're going to do, because you will be doing the same thing over or in the same scenario, right? So you get predictable. But in technical problems, this is not what we are looking for, right? We are not playing poker. We try to control systems, for example. And in that case, we expect that this acting deterministically is fine. And usually deterministically is the optimal choice in most cases, right? So for DDPG, this setup is basically the same. We also will have an actor and a critic. Actor and critic. Only in this case, the critic will output the action value function. So Q of X and U. So it needs the information from the actor, which will be U, the action that we're going to take, and of course the same in both cases, the state or observation X. Yeah? So how to train the critic is something, yeah, it kind of falls, you come up with it right when you see it, right? Will be just usual supervised learning on TD0 updates, right? So you just train this critic. Yeah, let's think W is what Oliver always uses for the critic. So you will just have this update formula, QW of XK, UK minus RK plus gamma Q. Here we'll put a question mark for later. We will talk about the later. XK plus 1, UK plus 1. And then squared, right? So I just update the weights of the critic by waiting one step and seeing what falls out. So the usual bootstrapping update step, right? You have seen this already in the past. So how to update the critic is not any different here than from updating the critic here. The only difference is that here we have a state value function, here we have action value function. but actually the update step looks the same. But it gets more interesting for the actor, because now we can compute a deterministic gradient. That's hence the name, deterministic policy gradient. Can calculate the gradient from here to here, right? This is a continuous function that we can where we can calculate the derivative, and this is also a continuous function where we can calculate the derivative. So we plug this function into this function, and we just have to apply the chain rule to find the derivative concerning the weights of this network, of this actor. So we could say this is policy pi with parameter theta. And then, simple as that, we can just compute the gradient of Q concerning theta, because they are in line, right? Questions to that so far? This one. This would be Q of k plus 1, so to say. So yes, here we have U of k plus 1. So, of course, we would need to know this as well, right? How do we come up with that? We just use the actor again. So it's just bootstrapping, basically, right? Here we would need to know which action will be taken in the next step. But the action that will be taken in the next step will also be taken according to the actor, or could be taken according to the actor at least. So here we can just put pi of xk plus 1. But also for this pi, I will put a question mark to the parameters. Because if you compute the gradient concerning this, the gradient concerning w for this case, you only want to compute the gradient concerning this part of the function and not this part of the function, right? Question.
Where do we get the xk plus 1? Does it result out of the applied first u of k, or?
Yeah, this is from observation. So this is what we measure. Yeah, so just wait one step and then we can perform this. Otherwise, we don't have it, right? Otherwise, we would need a model, and then reinforcement learning would be obsolete most of the time if you have a good model already. Yeah, exactly. This is from observation. But apart from that, if we want to perform an update on the weights W of Q, then we want to perform it in that way that this function approximator is moved closer towards the target. So this is what we want to estimate, right? So we want to move this in the direction of this and not the other way around. So we cannot, or we don't want to, apply the same gradient to this one, right? Otherwise, we would move this closer to this side and this closer to this side. This is not what we want. The bootstrapping assumption that we make is that this is ground truth. It is not. I mean, we know that it is not. This is a function approximator. This is a function approximator. This might be very wrong, but from the very beginning, we have to assume in each step that this target is correct in order to optimize this function approximator. And then subsequently, over many iterations, also this target will get more and more correct by applying the correct weights here. And we will come to that in a minute, because it will be also part of the programming task. As I just said, we don't want to calculate the gradient concerning this and this, but only concerning this, because this is what we want to adapt and not this. Okay. So far, so fast. Any questions concerning this? Was basically just a review, but just in case somebody got confused here. Yes, please.
And once again to this xk plus 1. So I thought we were in the step k, and we want to calculate gradient for xk and 2k. How do we get xk plus 1?
No, we are already at k plus 1, so to say. So I mean, this
Can we calculate the gradient on this for the last?
You could also write it down like this if you feel more comfortable with that. So this would also be fine. The message is you make a step, you have one state transition, and from the state transition you can learn by calculating the actual deterministic gradient.
For the first Q values, we use the old X and Q values from the last step.
This one? Yeah. I mean, this is for which you optimize, right? So I want to know for this state and this action what the Q value would have been. And this sample of actual reward. I mean, at this point, I don't have any interference with my system yet, right? This is what I get back from my system. So this is what I need to take into account, or what I want to take into account in order to make this more accurate. Here we have our discount factor. And yeah, this is then the future action value to go, right? So here we have the TD0 update step. And for updating concerning the policy, we can actually just calculate the gradient right away, right? So we want, what do we want? We want to update the policy such that a better action value falls out at the end. So we want to increase we want to increase the action value, and this means we just calculate the gradient of Q concerning theta. Q is dependent on W. We plug in some X and some pi of theta of X. So performing this kind of update, applying this gradient to the weights theta should increase my action value in the long term, right? So this is what all I need to do. And in this case, I can just do that because this and this are continuous functions that are well defined that I can calculate the derivative of. And therefore, I only need to apply the chain rule, which says gradient of the inner function times gradient of the outer function concerning this this variable. So this would then be u qw of x and u. Just the chain rule in a multi-dimensional space, of course. So that's why we are using gradients. It's not probably not a scalar. If it's an easy problem, then it might be a scalar, but most of the time it won't be. And yeah, this is just a chain rule for that case. So this is how I update the actor. This is how I update the critic. And all I can get out of that is just deterministic policies, right? Because there's only one distinct value coming out of that actor network. And I cannot easily put in some probability distribution there. Because then I would kind of have a gradient over distribution, get something like a distributed gradient. Maybe concepts exist for that, but this is far from trivial. So for all I know, this is the deterministic part. Okay. Questions? Okay. Then let's get going. So this was a little review of the actual algorithm that we want to use. Here's again the update rule. So actually what I wrote there on the right corner. Here in the exercises or in the script, the follow-up state is always marked with a prime, right? X prime is the same as, now it says xk, and x without a prime is now in that case x of k minus 1. But I think you get the idea. If not, of course, always interrupt me and ask. Okay, so now that we know what we need to do, we need these two neural networks, an actor and a critic. And we will do that in this exercise using the PyTorch environment, which has the same concept of TensorFlow, basically. So TensorFlow is for making functions or making neural networks, and PyTorch actually has the same idea. But many people say that PyTorch is much simpler to learn. So at this point, we decided to give you also an overview of PyTorch, not only TensorFlow, so that you can decide yourself whether you are more comfortable with this or with that. So we define just a simple function that builds us a multi-layer perceptron. Nothing too heavy, honestly. I mean, this is also the code that was given to you already. Some plotting routines so that we can evaluate the results later on, and then some testing routines so that we can evaluate whether or how the performance of our agent is. Then here we initialize or the classes for actor and critic. As I said, we can now use the multi-layer perceptron function here in order to define the actor. The forward pass is just execution of the network. So pi is the network itself in this case. We put the state into it, we just execute the actor, and then we have some state limits that we, or some action limits in this case, that we apply to that. So the output of the network will be between 0 and 1 maybe, and the actual input of our control system, or of our rocket in this case, might have some different action space limits. So not 1, but something else. We are counting for that. And this is the forward pass. We need this with a gradient, so to say, for when we are training, and without a gradient when we are just acting, right? If we are doing the test case, then we are not really interested in the gradient because we are not optimizing any longer. So therefore, we can perform the same operation without a gradient, which will not change the result of the action, of course, but it will free up some resources on our computational hardware. And there are actually many cases where you want that, although maybe not in this computer exam. But if you consider that you need to buy actual hardware for executing large neural networks, then it's nice to have any resources freed up that are available. Yeah, and actually the same kind of routine applies to the critic. We have the definition of a multi-layer perceptron, which can look just the same, with the only difference that we know that there's only one value coming out in the end. So for the action, or for the actor, of course, the output has the dimension of the action space. If we have multiple actions possible, or multiple dimensions, then of course we need multiple outputs. But we will only have one action value. So therefore the output of the critic will only be 1. So this is hard-coded in here. The case that we don't need a gradient doesn't apply for the critic. We do not need the critic to just control our system. We only need it for the training, kind of. So if we are finished with the training, you can basically throw away the critic because it has then done its part already. So therefore, we don't see a part where it says no gradient here. So what is happening here is you're just applying the multi-layer perceptron, which is the critic, and plug in the state and the action. Simple as that. We are using a replay buffer for the DDPG. I think you've come in contact with that before, maybe? Can someone tell me what the replay buffer is? No? I'm not sure. For the actor critic algorithm, there are implementations where it has a replay buffer and somewhere it has none. So if you haven't come in contact with that before, What would you expect could a replay buffer be from the naming of it? So what is a buffer? Some sort of memory, right? So what could replay mean in this case?
That we reuse the data.
We reuse the data, exactly. So if you sample some trajectory on whatever environment, you sample data, right? This is now our scalar state, for example. We sample this trajectory, and this is maybe the data that we get out of it. If we use this data one after another, one sample after another, to update our algorithm, update our policy, update whatever, then we have the problem that data will be correlated in the sequence we get it, right? There is some correlation between this data point and this data point because they are sampled directly after each other. So it's not really so informative for me to use them directly after each other just because that's the way they are arriving. So it's better for me to just put them in some memory, make the memory as large as possible. Large, of course, also according to your computational resources. And then take just random state transitions out of this so-called replay buffer. Because random state transitions, for example, taking this and taking this, they will be correlated, right? They will be much more correlated than taking this and this. So this one will be more informative for me because there's not so much information about this data point in that sample, about this data point in that sample, so to say. And if I now extend this to a much larger replay buffer, so we have many more samples following after that here, then I have also much more possibility to sample informative state transitions where there's not so much of a correlation. And this makes it better. And also, I can reuse data more than once, right? If I'm fast enough with my training, so if execution, controlling the plant and training from this data is independent from each other, then I can take some advantage from having an already filled replay buffer because I can learn from the same state transition more than once. Yeah, take information out of that more than once, so to say. So this is the idea of a replay buffer. So basically just some memory where we save our state transitions, save some history of what we did and what we measured to use it later. So this is actually the whole magic that happens here. We just free up some space where we can save stuff in for later. So we initialize the space, we make a push function, so where we just put in new samples into these arrays. This is here done with the pointer variable, so there's always a pointer that is counted onwards. And once it reaches the end of the list, then it starts at the beginning again. So it's some ring buffer to have the size limited because you don't want data structures of increasing size. We set the size once, we allocate the data once, and then once we reach the end of this of each list, we start at the beginning again. It's a ring buffer. It's also important because if you are training for a long time, your policy will change over time, and the sample data that is in your replay buffer that you sampled a long time ago is not anymore has not anymore so much in common with the policy you are right now acting on. So if your data is very old and your new policy would never collect such data because it's not going anymore to such states or not anymore taking that action, then it cannot learn so much from that because yeah, the data is has just aged, so to say. Yeah, and then some fetching function. We can or we define a batch size here. So how many of these state transitions do we actually want to take? Oh, why is nobody saying something? how many of those state transitions we are actually trying to take. In our case, it's now 32. So we try to select 32 random, this is important, random transitions from our replay buffer, and they should be random because they should not be correlated. So we try to distribute them kind of evenly around our replay buffer. Questions concerning the replay buffer? There was some other exercise where you were building a model for the system. You could also, yeah, this is kind of helping in the same way, right? You are trying to increase the number of samples that you can use later on. So, and now we can define the actual DDPG agent by plugging it all together. Actor critic, batch size as a parameter. Not so interesting, I think. Here we need to make use of the functions that were defined above. So we now set the actor with a specific observation dimension, action dimension, with a network size, activation function. I think this is also not too surprising, but yeah, it needs to be done. Replay buffer, just the same, with its specific buffer size. So buffer size is not batch size. Don't confuse this with each other, yeah? Buffer size is the history of data that you are collecting, and the batch size is a subset of that you are considering for your updates. And then we are defining these target networks. What are target networks? One second. Just as a small reminder, I had these question marks put on here. These have to do with target networks. So who can tell me why do I want to have target networks and what is their task? I actually told you in which problem I run if these weights and these weights are the same. And I compute the gradient concerning both of that.
Yeah, as you mentioned, we want to adapt our QW network to our target and not both into each other's direction.
Exactly.
So the other one has to be independent, or at least not dependent at the actual moment from our Ws. So we, from time to time, update our target network based on our actual network, but it's not the same network.
Exactly. So you can imagine the target as the lighthouse and this critic as the ship. And the ship is trying to find the lighthouse and not the other way around. If it would happen the other way around, you would know that something is wrong. The lighthouse is moving, cannot be correct. The next problem is, if I update, or okay, now I calculate the gradient concerning this, only this critic, concerning this cost function, but only concerning this function actually. Then I perform the update, and after I performed the update, then still I alternated the target, right? Because even if I only calculate the gradient concerning this, the update will also affect this. Not the gradient, but the update will. So what I will get is a moving lighthouse still. And this is where I use target networks in order to slow down the rate at which the weights of the target are updated or changed. So let's put a tilde here. and a tilde here, so that we know that these parameters are actually not the same as these parameters, at least not all the time, or probably actually most of the time. So how do we do that? To look whether it was in here or if I write it out. No, let's write it out. The idea is, or one possible idea, and in my experience, the simplest but also most useful one, is to just plug or just put Poliak averaging on it. Poliak averaging is just a fancy word for low pass filtering. So we do not update both of them at the same time, but we low pass filter what happens here and apply only a low pass filtered version to that to have the updates of this slowed down. Update rule looks then like that. Iteration plus 1 is minus tau plus W tau. So tau is very small. Tau is just a very small number. So we are kind of reusing most of what is in here. And of course, these are all vectors. Reusing most of what we had there before. And just, yeah, use a smaller part of the new W that we calculated according to our gradient step. And this will slow down the lighthouse and makes it much easier for us to go there. Because if it would be moving around, then also our ship would need to be moving around, which is not what we want.
One question to that.
Yes, please.
What's the example of the lighthouse?
Yeah.
So the lighthouse is not moving anymore.
It's still kind of moving, but much slower.
But it's still at the wrong location because, especially in the beginning, our estimate network is very bad, right?
Our estimate network is bad. Yeah, exactly.
So we have not moving lighthouse, which is standing somewhere in the sea.
Yeah, yeah.
Guiding us to the right direction.
Kind of. It is, as I said, it will be moving, but it will be moving much slower. It will be moving into the correct direction because this is what we expect to be the correct direction, right? We expect our updates to be useful. So we expect our true W that we are calculating here to be helpful.
But why is it helpful if the target which we aim for is bad?
That's the basic concept of bootstrapping. By updating this in step 0, we are updating this, or we are alternating what we get out of here in step 1. But this update should not be too large, because if my lighthouse is first, I see it here, then I see it there, then I see it there again, then I would be going around like that. So I'm kind of, without using target networks, I would be provoking oscillations in the parameters. And oscillations do not help me because it could happen that I'm just moving also around my actual local maximum or minimum, whatever you are aiming for, moving just around that, just stepping over it, then stepping over it the other direction. This is what we are trying to prevent by using target networks.
I understand that we are not moving like so we're moving in a constant direction, but why is that direction correct? I still don't understand why our estimate is improving if we use bad targets. It's like, I imagine if the coast is there, but my lighthouse is there, and I learn to go that direction, I don't reach the coast, even though I'm not oscillating around my lighthouse anymore.
Yeah, but the lighthouse is also slowly moving into the correct direction.
But the lighthouse is dependent on what I learn. So, okay.
Yeah, okay. Maybe in that endeavor, the metaphor doesn't work out anymore. Maybe we just have to accept that. The takeaway message is that every time, and here maybe let me allow myself to use the metaphor once again. Every time we are steering or controlling the ship, we would be moving the lighthouse also. And this makes it very hard to steer, right? So imagine that with your car. It's hopeless in that case. we slow down the change of the target of all that here in order to give our optimization algorithm a better chance to have a more directed way to the minimum. And if this minimum turns out to be bad or to be not correct, maybe it's in any case better than where we are now. Maybe it's not correct yet, but we are slowly getting there. And at that point, also the target has slowly adapted, and then we can make better decisions from there. Another, Jaron, question?
Yeah, why two sets of targets there? If we're only applying this to the actor.
Sorry, no, we have it for both. We have one for the critic and one for the actor, because both of them play a role in calculating this right-hand side here, right? So
it's calculated on all the actor, all the delayed actor.
This action is calculated in the delayed actor, but this action is never performed on the actual system, right? Because on the actual system, we also want to use the actual actor. So this is something that we only have in the background. We will never see the real world influence of this, so to say. Yeah, bootstrapping. It is hard to grasp that, I know that, but it actually works. It is how it works, right? And if you do not use target networks, it still works, but it will, or in many cases at least, it will still work, but it will take you longer because you make of kind of large oscillations around where you actually want to go. And if you can dampen these oscillations, dampen means using a low-pass filter. If you can dampen these oscillations, then you have a more easy life, easier time to actually go to the minimum or maximum of whatever function you are trying to optimize. Of course, in this case, we are trying to minimize because this function is an estimation error and we are trying to minimize estimation error. Try to maximize estimation error will not be good. Okay, further questions? Mm-hmm.
Is there anything that I check for these two networks, the data I'm choosing? There is a correlation or not before trying this policy?
Good question. There is something like that, yeah. It's not part of the course, and I have not encountered it yet, but there are concepts like that where you are trying to look for the most kind of informative samples inside of your replay buffer. But for the best I know, this is still very much researched at the moment, so I cannot give a final answer on that. So as far as I know, there's no simple answer on that. There are many concepts that try to do that, but it's not straightforward.
It's kind of having an assumption that I am taking short time correlated data, and because I'm delaying it, so there is no correlation. It's like an assumption. I'm not checking the correlation before starting.
No, but this is not the concept of using the replay buffer. This is not what is meant by using the replay buffer. We have a very long trajectory, which fits into our replay buffer, for example. And now we are just using random data points out of whatever is in our replay buffer. So I might use this state transition. I might use this one. I might be unlucky, and because I'm drawing them randomly, I might be unlucky and also get this state transition. But globally speaking, if my batch size is large enough, that I sample from this replay buffer, then on average, I will have not so many correlated data in there, or not so many correlated state transitions in there. This is only for one learning step. In the next learning step, I'm sampling a new set of, or a new mini batch, which is again completely random. and which takes into account one more experience, one more data point that I sampled in the meantime. But yet still, it's a valid question. You can still try to find the points in here which have the least correlation or which give you the most informative update in the end. But it's not easy, unfortunately. Good question. Further questions? Replay buffer, target networks, actor critic. It's complicated. Let's agree with that. Okay, target networks. And you see what we are doing first here, deep copy of the actor. So our initial parameters that we are applying to our target networks are actually the true network parameters. We are starting out on the same base, and then we are just updating these ones much faster than we are updating these ones. On a side note, this is only one possibility to do it. You could also, so this Poliak averaging or just low pass filtering. There's also a different way of doing that. You could perform hard updates. You could say, okay, I will now do 1,000 steps of sampling and training, and then after 1,000 steps, I do one update where I just copy this variable into this variable. And then for the next 1,000 steps, I keep this constant again. This is also a possibility that you could take. Maybe easier to implement because you don't need to know this function. But okay, on the other hand, this function is not too surprising. To my experience, this is a very, very advantageous way of doing it. But hard updates I also encounter once in a while, so it also is valid. Okay. We set the optimizer, which is the Adam optimizer in this example. So gradient descent with some extra steps. We find the action space, also nothing too complex, I think. Now we need to compute the Q-loss function. So the function that we need in order to update the critic, which is basically this function, but on a batch. So we use many samples and have many of these, so to say. Hope you can read that. So herein is a batch of states or a batch of actions, all belonging to each other. So these are state ranges. The data is belonging to each other. The actions that I find in this array are the actions that I made in these states. So these are connected to one another. And then where is it? Yeah.
The action there is always the action put out by the actor.
Yeah, so this is an actual sample that we have taken from the actual environment. So this is a measurement. Yeah, this is an action that has been performed by the actor. Although it doesn't really matter whether it is from the actor or from another source, right? You could take a sample that was taken in a different experiment and still try to take information from that. You have no guarantee that this information will be informative for what your actor would be doing now, but you could still try doing that. So it's an off-policy algorithm. We are not dependent on sampling on the same policy where we want to learn on. We could try using samples from a different policy. So it's possible. But what I want to say, the time correlation is still the same. So if I have here, or all the actions that have been taken here are the actions that have been taken in these states. So these are connected to each other. This is not completely random, otherwise it won't make no sense. And then I'm calculating the backup, or I call it the target, using the target critic. So Q is the critic, or yeah, critic target, and the actor target inside of that. So this is actually the same as this, right? Q with target parameters. I plug in the next state, because the previous state would be, in our case, x of k minus 1, which is, but here we need to put x of k, so the next state. And then the same applies for the policy, pi of theta target. So actor target. And then of the next state to find out which action would our target actor perform in the next state once we are there. And then now here, you see that our backup, so this whole target, also accounting for the reward that we have seen there, we have this factor of 1 minus the terminated flag. And the terminated flag tells us whether our problem has come to an end or not. Why is that important to have that in there? Why is that interesting? I didn't write it down, which is a simplifying assumption, but here we have it, and it's actually a good idea to have it. So what would happen if our problem goes on? Yeah, please.
So the terminated flag would be 1, and it is terminated, therefore we would multiply with 0, and our backup would be only the reward.
Exactly. So why is that?
Because after seeing this reward, we are in a terminated state probably, and therefore it's not going on any further.
Yeah.
To calculate Q values for it.
It cannot, our problem just does not go on, right? The basic concept of reinforcement learning is trying to find the discounted but accumulated reward for the end, until the end of time, right? It's for an infinite horizon. But once we reach the terminated state, it does not make sense to have this considered anymore, because there cannot be any more reward to collect. So therefore, we nullify the right-hand side. We nullify this, because this reward will be the last one that we see. And after that, we would need to start over. We need to reset our environment, and then we can start from 0 once again, so to say, from a new initial state. But yeah, once we are terminated, it would be a false update if we would consider this target once again, because we can never go there actually. For the framework we are using, we do not only define the terminated flag, but we also define a truncated flag. Have you considered that yet? Yes, no, maybe, maybe not. Okay, what terminated means is kind of evident from the name, right? If I crash my car into the wall, then the problem has kind of terminated. There's nothing more to do. If I land my plane on the ground safely, then this is also a problem that I have terminated safely, but it's terminated. There's nothing more to do. If my task was to land the plane on the ground and I did that, it's fine, nothing more to do. For practical reasons, however, we do not consider full episodes for all of the problems we are looking at, and for some of the problems there are no full episodes. There is, for some problems we can't just say that something has terminated. So for practical reasons, we truncate some of the episodes we are learning from. We just say, stop, I don't have more time at my test bench. I must stop now, and I want to go home. This is important for this consideration, because because it should not have any impact on what you are doing here, right? Just because you are saying that you don't have more time to do this experiment, it could still go on, and the agent probably did nothing wrong, or maybe did nothing wrong, and could still go on and could still consider what happens in the future. It's just that I don't have any more time to consider that, or I just want my algorithm to run through in order to test it. If you look at usual control examples, for example, what we are doing, controlling motors, you set up the controller, you set up the motor, you let it run, but you only let it run for some time. At some point, you have to go home. Then you have a truncated problem. But this does not mean that you cannot give credit to the agent for doing the correct thing, right? The agent did nothing wrong. You truncated the problem, or I truncated the problem. The agent can only terminate the problem. But this is more or less part of the human-made problems around reinforcement learning. Yeah, and then here we have the actual function that we want to minimize or optimize. And yeah, as I already said, it's the same as what we have here, just that I didn't consider this part here. And what you also need to keep in mind, in most toolboxes that you will encounter for not only reinforcement learning, but machine learning in general, you will usually have optimizers that try to minimize the function, right? In this case, it is important to specify that, and we will see that in a minute also in the code. But this is a function I want to minimize because it's an estimation error, and I don't want to have error, right? I want to minimize the error. In this case, we are looking at value, action value, reward, state value. These are things that we want to maximize. So this we use for learning, we want to maximize. This we use for learning, we want to minimize. And if most, if not all, of the frameworks that you can use for that are always trying to minimize, I mean, this is easily accounted for, but you need to keep it in mind. If you forget that, then you are in the end doing the opposite of what you actually want to do and cannot expect it to work out, which is why we find this loss for the policy function. So pi, which is not only the critic with the action plugged in, but it also has this minus in front here, right? So the loss that we are trying to optimize is actually just this, Q with pi plugged in. But we try to maximize this. Our optimizer will try to minimize that, so we put a minus in front. So minimizing minus will make maximization in the end. So we get what we want. So accounted for. Questions to that? It's obvious once you have seen it the first time, but before that, it might be confusing to some. Yeah, deliberate function is the function that we use for training. So the first step that we are taking here is fetching data from our replay buffer. The fetch function we have defined above, so the fetch function will find random samples from our replay buffer. So again, this is our replay buffer. We take just some random state transitions from that. Not only one, but many, but it always must be state transitions. Only having independent samples doesn't give me any information. I need to know where I start, and I need to know where I go from there, taking one action in our environment. So this I write into data, and with this data, I will then compute the loss function of Q. So just this function for multiple samples at the same time, taking the mean of the batch. So put in like 32 in our example, 32 state transition. How could this word be so hard? Into this function, and then find the mean loss over this 32 transitions, because yeah, having a larger batch size kind of decreases the chance of having multiple very correlated samples sticking out there. I perform the backward pass concerning this loss that I calculated. So I first of all calculate the estimation error that I make in terms of this function. The backward pass gives me the gradient. So I calculate the gradient, and then last step here is applying this gradient. So only performing the backward will not change the weights yet. It will only give me a value for the gradient, and then I need to apply the gradient as well. So write new parameters into the places where the old parameters sit, which is done by performing an optimizer step, which we see there. Then I want to do the same concerning the policy. So this was only the critic. Now I want to do the same concerning the actor or the policy. Here it is, I don't know whether you can read that, but it says we don't want to waste computational effort, so therefore we freeze the parameters of the critic, because now that we want to update the policy, the critic will not be changed. So therefore we don't need to change the critic's parameters, and therefore we can freeze them in order to tell the system that it does not need to calculate the gradient for it, because we will not use the gradient anyway. So we tell it in beforehand, no need for that calculation. We can use this computation time in a better way. The update is performed in the same way for the actor as it was for the critic. You see it looks the same. These three functions are the same as these three functions. Then unfreeze the Q network, because in the next step, of course, once we start again with the update, we want to train again. So therefore, we should not forget unfreezing the Q network so that we can actually update something there later. And then, yeah, here it's also called Poliak averaging, but it's actually low-pass filtering, just a fancy word for low-pass filtering, in my opinion. We update also the target networks in the same way as already proposed. So we use most of the old parameters and some of the new parameters, and then get a whole new set of target parameters. And we do that not only for the critic, but also for the actor network, because we need both of them in order to calculate this right-hand side, this target that we need to find the estimation error. Yeah? So that's why it's also twice done here. Once for the critic and once for the actor. But it's actually the same operation that happens, right? You see 1 minus tau and tau times the actual parameters. Questions? No questions. Okay. I will go on. So this was the hard part. This was the training. The training is what is actually complicated. Now let's come to the easy part, the decide function, where we just need to make a decision, which action will we take. And as I already told you, for that we do not need the critic. The critic is only used for finding or for making decisions what is actually the best action to take. But after I've done that, after my training is over, I can actually throw that away, because only the actor holds my information or the knowledge of what should be done. So therefore, this function does not use any critic. We only use the actor, the act function, where we just plug in our state, and simple as that, get an action out of that. And this is what we can apply then later on. For practical reasons, you see a clipping function here, because if your system, whatever system you are using, does not take any action space or any action limits, then of course you must be sure to respect those limits. So therefore you want to apply clipping. And of course, if you are training, you would also want to use this random part here. So there is a random noise added to the action that we are applying. Why is that? Why would I apply something random, although I'm expecting the optimal policy to be deterministic?
To have exploration.
Exploration, thank you. Yeah, very important, right? We need exploration. We need to try out something new. If we only trust in our policy and it sends us into the same states over and over again, we wouldn't learn something new. So in the training, we also would like to have some exploration noise, please.
So just to clarify, that is the decide function now part of the training, or just after we finish training, we use the decide function to get an action?
We use it also during training because we need to get our samples from somewhere, right? So if we are training on policy, the algorithm is able of training off policy. But if we want to train on policy, then we are also using this decide function during training.
And in training, we use the noise, but if we are not training anymore, we don't want any more exploration, right?
For most cases, yes, exactly.
Okay, then we would use the deterministic.
Yeah, exactly. And so why do I call it a deterministic policy if we are still using any noise here? Because the nature of the noise is not trained in any way, right? It's superimposed. It comes from outside, so to say. The agent does not know that there will be any noise in, later on. We tell it, or we define that noise. In actor-critic methods, you have the noise as part of the network output. So it's kind of trained. You can train which variants you want to have in there in the end, or the algorithm will tell you which variance is helpful to have in there in the end. In this case, this is not done, right? Nothing of this is trained. These are just fixed variables that we from the outside fix in beforehand, or maybe even schedule during training. We can, of course, fit them to whatever we want, but they are not part of the training. The algorithm doesn't know of them. So what we are actually training will only be the deterministic action that will be taken in the, or that we also want to take in the end. The exploration noise is not accounted for in the algorithm. We need it in order to find new samples, but we don't have it optimized in any way. Yeah? Everybody happy with that so far? I know it's not easy, but I think the challenge makes it interesting. Okay. So I think, yeah, exactly. We are finally ready to go and use that. Yeah, the parameters of what we are then applying here are listed. I think I don't need to go by them into detail, and how the simulation routine looks. You've also seen a lot of times. So I think let's just have it run shortly. Huh? Shouldn't it be doing something? This looks strange. Anyway, I had this, as you see, I had this running before, and so it doesn't really matter. So just imagine that there would be some simulation going on right now, and there would be some loading bars filling up. And after we have 4 different trained agents, the result will be looking, or could be looking, like that. So we have, can I increase the size of that a little more, maybe? So we have in red, the red line up here is the best available or the optimal computed reward that you could get out of that. Right, you see here the accumulated rewards on the left axis, and the number of steps on the right axis. So we didn't go about that so comprehensively, but the basic problem is that if your actor decides to not use the fuel on your rocket, then the rocket will just sit there and sit there and sit there. And so we cut this problem at some point. So this means if the number of steps rises, then this means that we have a policy that is not using the fuel at all. Bless you. That is not using the policy at all. So that's also why if the number of step rises, the reward is actually going down, because if we are not using the fuel, we cannot expect to go very far, very high with the rocket. So the red line is the analytical optimum of this problem. So if we find an agent that is able of hitting that optimum, of course, it did a very good job. The orange line is the best we could achieve with applying random actions. So somebody performed an experiment where only random actions were performed out on this environment. And the best result you could get with that is this orange line, or in this experiment.
The best reward or the best number of steps?
The best reward. So for the reward, for the left axis. Where was I? Yeah. And so we would hope that we are better than the best random policy, right? I mean, a random policy can be very bad, can be very good, but only applying random actions on that is not really a policy, right? So we would expect to be at least above the orange line, and in this case, it worked out. The yellow line is the average that you get when just applying random actions. So we would expect to be above the yellow line all of the time, actually. But we see it does not work out for all the time of the training. So training time is on the x-axis. And we see that for some time here in the intermediate training, the agent is not really good at all, and then it gets better once again. Looks kind of similar for this one. This one really good, made it work right from the beginning and just stuck with that. Although still it's not hitting the upper, the optimum rewards, but it's only over there in between the orange and the red line. And last but not least, I also had an agent in here which did the job completely wrong. You see, nothing good reward, no good reward is coming out here, and the episode length, so the number of steps, is actually hitting its upper limit for most of the time. And if that happens, then the reward is also not that great, of course.
Why did the agent change something when you learned after 20 episodes it's not working? So you kept running into the limit.
Yeah, there's always room for improvement, of course. Can be many reasons, right? If you are starting out with a very unluckily initialized policy, and you need to move far away from that initialized policy, then you would need a large step size in the beginning. If you put a very large step size and keep it constant for the training, then you cannot fine-tune very well in the end. So it's always some compromise that you need to take, and some hope in the optimizer that it will fine-tune the learning rate according to what you're trying to do right now. And in some of the scenarios, it just doesn't work out. Sometimes you get unlucky. From my experience, you always find some set of hyperparameters that will work in any case. But finding the set of hyperparameters is also a lot of work, right? Finding the correct network size, maybe the network size that was applied here was not available, or was not able to map the complexity of the problem in all parts of the state space. And if you happen to be in those parts of the state space a lot, then of course you're unlucky. You never know. So in the end, I would guess that there is a set of hyperparameters which that we would not see something like that. But for the given set of hyperparameters, we got unlucky for this case. And yeah, didn't work out. Maybe it's also just a matter of time. If we give it more time to train, more episodes, it may work out in the end. But human time is limited. And also money, right? If you do this on an actual rocket, would not be great, maybe. Yeah, training is here once performed episode-wise and once step-wise. Just the difference of in which order you and how much you perform each action, but in the end, each code snippet. But in the end, the training itself looks the same, so the routine looks the same. So here are some results for that, some numerical results. So the worst reward you could get is -1, which happens if you stay on the ground for all the time and then hit the time limit, then you get a reward of -1. The optimal control output, the optimal control reward, so what you would get if you did it in the analytically best way, would be 0.0122. But unfortunately, we see that none of our agents is able to hit that yet. And yeah, in that case, this fits to this one. In that case, the last one, yeah, did nothing good at all. So in the actual test case scenario where we then apply deterministic options, it also just got a reward of -1. So not a good policy. I think we should be able to see some graphical output here. I fear that something broke down here because I didn't do some action on my computer for so long. So I can't show you the animation right now. I will try to put it into the video later on. But yeah, I think you get the idea. Animation would just be animation in the end. So on a side note, stable baselines. There are many frameworks that plug in all the, or that publish all the functionalities that now was our job to implement. So, I mean, we went over a lot of code now. We needed to think about a lot of things. Target networks, replay buffer, gradient, all of that, plugging in one network into the other. And all of these concepts are, of course, you don't need to invent them by yourself every time. There are many packages also in Python, or mostly in Python for all I know, that implement already a lot of the reinforcement learning algorithms that we currently have available. One of these is Stable Baseline 3, which actually performs the same job that we did in so much code now in this much code. Of course, just showing you this in a reinforcement learning course would be kind of boring because we want to know what happens inside of that. But basically, we can just, so actually this part of the code is only for making the loading bar down here. So it's only this part of the code that we actually use for training the agent and applying it. We can just have a class that is named DDPG from that library. We define everything according to their interface. So we have a MLP policy, which is a multi-layer perceptron. Probably there are other policies that use recurrent networks or whatsoever. There are other architectures that you could use. We define batch size. We define that we want to learn on our CPU and not on our GPU. If you want to do image classification, then you would use GPU, but for reinforcement learning, this is usually not what you are doing. You define all that, and then you run it. And then you get also a deep deterministic policy gradient agent with policy, with just a fraction of the code that you would need if you wrote everything from scratch. But of course, writing everything from scratch is what is interesting here. because using a library is nothing that you need to study for in most cases. Yeah, and looking at the result that these libraries achieve, it actually looks a little bit the same, right? It does not look so much better than what our handwritten code achieved. So we have two scenarios where it looks kind of good. Here actually it breaks again in the end, and then we have two scenarios where it's not looking so good. So you could also question whether there's I mean, of course, one could expect that there's big of an advantage of just downloading a library where many people looked over maybe, which is open source available. Open source always good, of course, but on the other hand, I like knowing what goes on in my code, and therefore looking at it and looking at what is behind the code is also a good thing to do. That was DDPG. We are already on our time limit, almost at least. If you need to leave, of course, you feel free to leave, but I will go on talking about the PPO, proximal policy optimization, which we have seen today, and have a look at that at least shortly. So, first question, what was the idea of proximal policy optimization? Why, if we have something so powerful as DDPG, where we can just directly compute the gradient that we need to apply to the actor, why would we need something else? I mean, we have seen that there could be interest in something else, right? We've seen these kind of episodes. So if you try to remember today's lecture, what was the idea of PPO? What did it implement in order to tackle that? Try to force the updates to be good. Maybe someone else. Yes.
We tried to reduce the effect an update can have in the action space, so that we cannot change the policy effectively for the actions that much in a single update step.
Exactly. So if our current policy is average, it's not too good and it's not too bad, and we perform a huge step into either direction, then we have also a balanced chance of making it much worse and also making it much better, right? So we try to catch that kind of. We try to stop it from going this risky way and have the updates clipped. And if the update is too large, then we just clip it and say, okay, this update is not useful for us because it might actually not improve our policy. It might actually harm us. We throw it away. We don't use it. Yeah, and then of course we also had this discussion in the lecture concerning why we use the minimization operator. But I give this over to Oliver, and he will talk about that in the next lecture, I hope. Yeah, so another question concerning this algorithm. Is it used for stochastic or for deterministic policies? So DDPG, I already told you, it has it in the name, right? Deterministic policy. Looking at these formulas, can you make any sense of that? Why it must be deterministic or why it must be stochastic? Specifically this formula? Specifically this operation?
Yeah, it must be stochastic because we, for our policy pi, there is a likelihood distribution depending on the state. So it doesn't. So it's not the policy there is not deterministic.
It can't be deterministic, right? This fraction would not make any sense for a deterministic policy, right? If we would have a deterministic policy, then we would always have, whenever there's a change applied, we would have 0 over 1 or 1 over 0, right? Because deterministic means we are either we are sure to do this action or we are sure to do not this action. So the probability, and in this case it must be then the probability, can only be 1 or 0 in a deterministic space, so to say. And therefore, this wouldn't make any sense, right? 1 over 0 is mathematically undefined. 0 over 1 would give us no update at all. So it only makes sense if we have a stochastic policy in there. So is it better or worse than a DDPG? Nobody knows. I mean, of course, the idea is good to have the updates clipped in that way, such that we are only taking small steps, so that we are kind of seeing whether we are improving or not before actually taking all of these steps. But on the other hand, you must also consider that you would need more steps to go the same distance, right? Because the steps are just limited. And if time is your issue, maybe not consider PPO. If safety is your issue and you need to be sure that once your time is over, you have something that is maybe not great, but at least applicable, then PPO might be better. If you know that you need a stochastic policy, DDPG is not the way to go at all, and therefore probably PPO or actor-critic algorithm is where you want to be. Okay, I try to move over the code a little faster now. Because I think most of you will be able to read over that anyway. So we use a rollout buffer here, which is not the same as a replay buffer, because in a rollout buffer, we kind of only have the full episodes or the full trajectories. Kind of as in Monte Carlo learning, right? Where we firstly need to reach a terminal state or reach the finish line before we can start learning. And the same idea we have here with the rollout buffer. So we fill that buffer first, and then we learn from the whole path that led us there. Here, this block, which says advantage calculation. I mean, all of us know what advantage is, I hope. But I think this block of code looks overly fancy, having a function in here which says tree U. I would not even know what it is. I looked it up. It says upper triangular. So what you are trying to do here is before you have the rewards involved over there, you are building up a matrix of this form, which says over here, it says 0, gamma, gamma squared, gamma 3, then 0, 0, gamma, gamma squared, and so on, and so on. So this is what this function is trying to do. And if you picture it this way, I think you can also get the idea why we are doing that. If we are looking at the first state, then this is the way to go. This is all the rewards that we will be collecting with their corresponding discount factor also already accumulated or already accounted for. And if we're in the second state, then this is the return that we can expect from the future. So I must admit this code snippet and some other parts of the code are not that easily readable, but we are trying to get there. Yeah. So here are some things that we have already seen today. We have a multi-layer perceptron for the critic. We have a stochastic actor for the for the actor, obviously. Where was that defined? Oh, I just jumped over that. This is this maybe we want to take a minute to look at. For the stochastic actor, we have as output logarithmic standard deviation, so something that is logarithm of the standard deviation. I think this is just fine to accept. And then we have a multi-layer perceptron in there to find or calculate the mean of a Gaussian distribution. Yeah, and this one is just the standard deviation is just a constant, and the mean of this Gaussian distribution is what we are changing. Yeah, and this is everything you need to know about the stochasticity of this actor. The rest is actually pretty similar to what we've already seen. So the forward pass, you need to find the distribution, or the logarithmic distribution in our case, makes things easier. And as you see here, if you want to hand out the or if you want to sample on a normal distribution, of course, in order to, you need to account for the standard deviation being here in here logarithmically, so you need to exponentiate it before using it. Here we see again our estimation error for the critic. Rewards to go is in this case not the same as we see over there, but we are actually taking into account a larger set of actual samples. So we have a larger trajectory, and we are extending what could come in place of this Q function, right? So for the simplest approach, I only have the reward plus gamma times that. But if I have the data available, if I have this roll-up buffer, then I can also have the reward plus gamma reward of the step after that, plus gamma squared for the reward after that, and so on. And this is what we call the rewards to go here. So it's the accumulated discounted rewards in the whole buffer. Yeah, here we have the actual important thing about the PPO. So here we see this clamping function. It's a little bit cumbersome. NumPy calls it clipping, PyTorch calls it clamping. It's the same operation in the end. So we define this ratio of probabilities, or in this case, it's simplified a little bit by using logarithmic probabilities, and then we don't need to define the fraction of them, but find the difference of them, and then have the exponential function applied because they are logarithmic. And then, yeah, we just clip this to either the lower ratio or the upper ratio. So simple as that, but keep in mind clamping and clipping most of the time means the same. You just need to look at the framework that you're using. Then we want to maximize again. The optimizer will minimize, so therefore we need to put a minus in here. And also here we have the minimization function, for which we discussed already today that it is a little questionable whether it should be here or not. But more to that later, I hope. Yeah, optimization steps we've seen today already, pretty fine. And then application. Yeah, some experiments. I think from feeling, I think we could say that this looks more volatile, more variant than what we've seen with the DDPG. But maybe we can just account this for the stochasticity of the algorithm. Maybe it's just, yeah, trying out. Maybe it's just more random than the DDPG, also in the training. And maybe therefore the changes in the accumulated rewards are so large. Something that you already see here, a little bit at least, is very interesting. Remember, the red line was the computed optimum, right? There should not be something better than the analytical optimum. And yet still we see that in some episodes, we get a reward or an outcome that is actually better than that. Let's look at some further tests. I think there was a function in here. Yeah, exactly. Yeah, so we performed some more trainings to then calculate the mean over that to see whether this is how stable that is, and we have this in the end. So we should, or I should have performed 50 experiments, but it took me too long, so I only performed 4 up there and then 4 again here. So this is only 8 experiments. You should do much more actually, but I think you get the idea. So the average of these trainings looks kind of stable, right? It looks pretty good. But also here we see there are many episodes in there in the best seen reward that are actually better than the analytical optimum. How can this be? Does it make sense? Okay, please. Does it make sense? No, it doesn't make sense. It really doesn't make sense. So always when you see this, you have to question, why is this happening? It doesn't make sense. From experience, we can say that this shouldn't happen, right? If the solution is analytically optimal, then there cannot be another solution that is better. It makes no sense. So why is that we are seeing this? The environment, the system that we are training on, is not a real world, is not a physical system, right? But the system that the analytical optimum was computed for is, yeah, nicely defined, so to say. It's defined in continuous, it was defined in continuous time because the problem is actually physically nice. I don't know, you can define it in continuous time and also solve it in continuous time. And then applying the policy that you computed analytically optimally in continuous time in a discrete time environment gives you the red line. But the actually continuous time problem must also be transferred to discrete time, right? Because we want to have a simulation of that on a computer. So it must be a discrete time environment that we are looking at in order to apply or perform reinforcement learning. And this discretization step is only an approximation of the real world. And in this approximation, some information gets lost, something is, yeah, it's only approximated. There is some error in there. The discrete time representation of the system is not exactly the same as a continuous time. And therefore, we get the outcome that we can actually better than the solution that was calculated in the continuous time domain. So we must, unfortunately, we must account this outperformance to the discretization error that we just have inherently from using a simulation environment. Maybe there are other discretization methods that we could have used in order to make it more accurate. But this is not what we are concerned with here, right? So just be careful if you apply this in the real world scenario, if you throw out this policy on your actual rocket. I guess everybody of you has one at home. If you do that, then don't expect it to outperform the analytically best policy. Critically thinking, right? Critic. Sometimes you have to be the critic. Okay. I think, yeah, and then we also have a stable baselines example for the approximal policy optimization, and somebody put 64,000 steps in here, which I also don't want to show, don't want to perform with you. Also kind of volatile. Sometimes it just doesn't work. Sometimes it works. The idea is plausible to use proximal policy optimization, but and I think this was also what Oliver said at the ending of the lecture, of today's lecture. In the end, you have to apply the algorithm that is corresponding or fitting to your problem. And most of the time, this is not a trivial selection. And once you have made that selection, then you must also consider that you have a lot of hyperparameters that you could consider in there. So there's no one-fits-it-all algorithm, unfortunately. Not yet, at least. Okay, I think that's it. Are there any questions left over? I guess everybody wants to go home. But if you still have some endurance, then feel free to ask questions. Okay, then. Thank you for being here today. Thank you for having visited our course. I think I'm done for that. Have a nice day. Bye-bye.